Okay, so hi, welcome to a video about finding inflection points. Okay, we're given this equation, g of x equals 1/4 times x to the power 4 minus 4x cubed plus 24x squared. For what values of x does the graph of g have a point of inflection? Okay, so points of inflection occur where the second derivative changes sign, so where concavity changes. So we're going to find the first derivative. So, oh wow, what is that one? Oh wait, no, that was right. Okay, we compute the first derivative, we take down 4, and it would cancel out, so it would give us x cubed minus 12x cubed x squared plus 48x. Then we take the second derivative, which is 3x cubed, 3x squared minus 24x plus 48. Now we're going to set the second derivative equal to 0 and divide the whole equation by 3 because we have that in common. X squared minus 8 plus 16 equals 0. Now we're going to factor it, and that is x minus 4 squared equals 0. And that would be x equals 4. So we have a candidate for a point of inflection, which is x equals 4. So we're going to check if concavity changes around x equals 4. Since it's a double root, we need to check if the sign of g double prime x changes around x equals 4. So we're going to try values around 4 for x equals 3. So g double prime of 3. We're going to go back here. Okay, 3, 9 minus 24 times 3 plus 48. This is the double prime, remember? That would be equal to 3. Now we're going to plug in 5. 3, 25 minus, oh, actually I'll simplify it a little bit more. 3, wait, no, not streamline it, I'll make it more clear. 25 plus 5 plus 48, that's 3. Both of them are 3. Okay, so the second derivative is positive on both sides of s equals 4. So the concavity doesn't change. Wow. Okay, so g double prime of x equals 0 at x equals 4, but the sign doesn't change. So that means there's not a point of inflection. So no other values make g double prime of x equals 0. So your final answer is that g has no points of inflection. So you might be wondering, how would an equation have points of inflection? So basically, in this problem, it's probably not the best example. There are no points of inflection in this one. But a point of inflection usually occurs when a function's concavity changes. So when it changes from concave up or concave down or vice versa. So mathematically, this would happen when the second derivative is either 0 or changes sign around that point. Okay, so if we had the function like, let's say, if it's x cubed, and we take the first derivative and the second derivative, we would find that equal to 0, and then we'd keep testing it out, like, oh, okay, 6 times, like, -1. That's -6. 6 times +1, that's positive, that's concave up. Okay, this is negative, concave down, positive, concave up. So there's a sign change from concave down to concave up. Since the sign changes, x equals 0 is a point of inflection. So, in summary, a function has a point of inflection at x equals a if it's undefined and if a sign changes as x passes through a. And I really hope this helped. So, yeah. Thank you.